All right, welcome to this video. Uh, in this video, we're going to take a look at some simple iterative algorithm analysis. That means we're going to look at some simple looping structures and see how we can analyze these using summations. And for the problems that we're going to look at as just some subject matter, we're going to look at some arithmetic problems. We're going to look at the problems of doing some integer addition and integer multiplication using binary numbers. Before we do that, let's take a quick look at the idea of loop analysis. This is something you may have encountered before, so this may be a review. In this case, we've got a simple loop here stated in pseudocode. This is, say, a for loop for I from 1 to n, with maybe one line in the loop body output I. Maybe we have a question posed, how many times is the statement output called? And this might be a simple resource analysis problem. And we can see on the right hand side there, I've got a summation capturing the solution to that problem. Well, the output function is called exactly once in each iteration of the loop, and the loop goes from 1 to n, while the index from our summation, we can copy that almost directly from the for loop. And when we have a for loop, usually we have the benefit of being able to do that, with a few exceptions. All right, so let's maybe look a little bit closer so that we can extrapolate this to other, maybe more detailed loops. The first question we might have is, how many iterations are there of the loop? Now again, as I mentioned for the for loop, this is fairly straightforward. In other cases, we might have a condition, while the list is not empty, things like this. And that means we might rely on some logic to determine how many iterations of the loop we're going to get. And usually determining the number of iterations is going to help us determine what values we write both above here as our final index, and then down below where we begin. So what is our starting index? Here we chose 1. Our final index is n. Again, here we're copying that deliberately. In other cases, we may have to calculate what we might want to write there. There are a few maybe important things to remember about summations in mathematics that are important. One is that we always increase the index I, or the index that we're summing over, and we always do it by 1, which is something that we are not restricted to in for loops. So or in looping in general. So if we have a loop that counts down, or we have a loop that maybe divides by 2 every time, something more sophisticated, we're going to have to translate that into the right summation logic, in which we have an index that only counts up by ones. Okay, we might see an example or two of how we can do that. All right, if we've determined how many iterations there are, and we've selected some index to iterate over, if that's going to be helpful, then the next question that we want to ask is, well, what is the cost of each iteration? And if we get lucky, then the cost of each iteration is going to be a constant, like we have here. In this case, it's 1. Any other constant as well, maybe 2, 3, 5, whatever your favorite constant is. Of course, we're more likely going to give this constant a name, like C or D, than have an actual numerical representation. But for my example here, I have a 1. That's the case if we have a constant cost per iteration. More often than not, we're going to have a cost per iteration that changes with the iteration. It depends on which iteration we're in. A good example of this, one that we might encounter, is that as you maybe loop through a list, the list might get longer or shorter. It might grow in size or shrink in size, and therefore operations that we do on the list may also increase in the amount of time or operations it takes, or decrease depending on the length of that list. So that's something we might want to be sensitive to. So I mentioned I want to take a look at a few arithmetic problems. So the first one I want to bring up is binary addition. So first I've got the problem stated as a very simple information processing problem. We have the input stated as two integers, n and m. And then the output here, of course, just being the sum of n and m. So pretty straightforward statement of the problem. I've also got a statement of an algorithm here. My algorithm is stated in pseudocode. It's not exactly the most straightforward algorithm. I didn't intend it to be very obvious because one thing I want to do is verify that it is correct. And so maybe for a moment we can just quickly go through and see, well, what is it exactly doing? And then we can go and see if we can test to see if this is indeed correct. So let's quickly go through here. We'll notice the first two lines are just setting up some variables for us to use. C is our carry value, and we're going to set our initial carry to 0. And then we're also going to have our n represent the number of bits that we're going to need to iterate over. Now to do this, I've taken this mathematical function that we use to calculate the number of bits to write down a number. So if you want to know the number of bits needed to write down the number n, you will need the floor of log base 2 of n plus 1. And so here I've got that same function here, the floor of log of n, or m. Here I'm taking the maximum of the two, the floor of that plus 1. Now we take the max there because we're basically just saying, well, which of these two numbers is longer? Which one takes more bits? So we're taking the maximum. We can think of this as padding the shorter number with zeros out front, leading zeros, basically making them both the same length. Okay, so we've used that. That effectively helps us determine what we're going to be iterating over. So again, this is, looking ahead when we start doing analysis. If we're going to write a sum, we've got those 1 to n here. That's nice. Well, what is our n? What is the value? Well, we've got it here, the number of bits to write down the longer of the two n or m. Okay, so that's what we've done here. That's got us set up. Now it looks like we're iterating over the bits with a little comment that we should be sensitive to here. Assume the least significant bit is first. Okay, well, all we're saying here is when we do our addition, of course, normally when we do things in normal iteration we go left to right, but when we work with addition, of course, we know we go right to left. We start with the least significant bit and we go to the most significant bit. And of course, when we're doing this, we want to propagate the carry as we go. So inside the loop body here, I have two steps. I'm going to calculate SI, that's the value of the sum bit at this location. And then I'm also going to calculate the carry that needs to carry on to the next iteration of the loop. I'm actually not going to look very closely at the logic that I've got there. All I'm going to state is that I've used some logical operators. I'm going to say the sum is the XOR of these values. I'm going to say that the carry is the OR of these ANDs. This is just a certain way that I've expressed it. And you might say, hey, I don't believe you. I don't think that's correct. And if you're saying that, then great. That means you're skeptical and you want to see proof. You want me to demonstrate to you that this is indeed a correct algorithm for add. So stay tuned. Hopefully we're going to be able to do that. Finally, at the end, after this loop, we have to do one last step. If there's something remaining in the carry, we need to make sure we register that. So I set the the n plus 1th bit. So this is 1 greater than the longest bit in the two original values. Of course, if we're adding two binary values, we could overflow at least one place value, and so that's what we're doing here. And if we do overflow, then we'll set that value to 1. If we don't, of course, then this carry value will be set to 0, and this additional bit would just be a leading 0. In the end, we just return S, the collection of bits. And again, the question we might raise, or the first one you might raise, is, hey, is this a correct algorithm, and can you prove it to me? And hopefully I will be able to do that here in just a second. Following that, we might ask maybe the more relevant question to this video, which is, well, how many operations does it take for us to do this? How many, in this case I'm going to focus in, how many logical operations is it going to take for us to do this add? Okay, so the first question is actually not that difficult to answer if we realize that all we really need is to calculate the truth table associated with those logical representations. So let's start here by just looking at the truth table that I've set up here. I've set it up to list all possible combinations of the three input values, if you will, for each iteration of the loop. So when we go to each iteration of the loop, we're going to be accessing the bits in location I. And so here I've got n sub I and m sub I calling out those two, the bits in location I for n and for m. And then we'll also have the current carry bit. Remember, we initialized that to 0 at the beginning, but afterwards it propagates from one iteration to the next. And here I've got just all all 8 combinations of the three variables that we set there. So maybe they're all zeros with all combinations going up to them being all ones. Okay, perfect. And then what I've gone and done is I've just using our simple logic, and please take time to verify that my logic here is correct. I've calculated the values that we used in our calculation. So again, maybe just going back quickly here, we did calculate the sum value. The sum bit that we should calculate in this iteration is going to be this XOR function. So again, taking a look here, that's this XOR function. All right. Likewise, the carry bit on each iteration was this longer value, which was we had some conjunctions here joined together with ORs, or a disjunction. And again, we have the same thing here. Okay. So if we want to verify it, what we need to do is, again, check my logic, do that on your own, and make sure that these values here are correct. But if they are, then verify with me at the moment to make sure that they make sense. So remember, this column that I have highlighted in red, this first one, this is supposed to be the sum value, okay, the bit that we add. And so maybe let's go through this very quickly. If I have a 0 and a 0, so if the two bits that I'm trying to add together are both zeros, and the carry from the last round is also 0, well, then the current sum would be 0. Maybe the next one down, if the two values I'm adding together are zeros, but I do have a carry from the last round, then my sum bit is 1. And then maybe going a little quicker here, we'll see that if there's exactly one value here, 1, 1, 1, then we should have a 1. But when we have two values, as in this case, the two values add to 2, we get a 0 as the sum bit. Okay, and again here we have 2, we get a 0 as the sum bit. Here we have 2, we get the 0 as the sum bit. But in the last final case, we get 3, so the total sum is 3, 1, 1, and so we get a 1 in our sum bit. So again, it looks like this bit is correct. So as long as that matches this XOR pattern, it looks like we have properly computed the sum bit for each iteration. Now let's go on to see, have we properly computed the carry bit for each iteration, and that's this final column here. Now that one's, again, let's go back to our combinations. We should have a carry bit if we have at least 2 1s out of our 3 variables. So we can go look, these first 3 ones are all less than 2, so zeros. But here we have 2. Indeed, our carry bit is a 1. Okay. Again, we have only 1 here, that's a 0, but 2, 2, and 3, all 3 of these have a carry bit of 1. Okay, so hopefully that is sufficient to help convince you that the code that we have here is indeed correct for addition. Again, if not, please feel free to ask a question related to this, and I'll try and respond. If not, let's move forward then from this question of correctness to the question of operations. So again, now I'm going to ask how many logical operations does this algorithm use? To answer this question, again, we're going to do some loop analysis. Outside the loop, we've got a constant amount of effort, so I'm going to, for the most part, focus in on the loop. So let's take a look at the loop here. How many times does the loop operate or iterate here? Well, this is again a straightforward answer. This is not a very difficult loop to analyze, so we know that this one's going to be a 1 to n kind of scenario. Because of that, we now only have to answer the question, well, how many operations are carried out inside the loop, in the loop body? And again, this is not a very difficult loop to do some analysis on, and since I've focused our analysis on logical operations specifically, I don't need to count things like the assignments and so on, the overhead that's involved here. I'm only going to count these logical operators that we've got here. Now, it looks to me like we've got 7 such operators. Now, I'm a little hesitant to say 7 because the XOR operator, it may be sort of a native operator, but it might also just break down into other operators, maybe a couple operators using a universal set. And because of that, all that I'm really going to try and confirm for myself here is that the number of logical operations carried out inside the loop is actually a constant. And so I said 7, it might be more than 7. I'm okay if I'm a little off on that. So I'm going to go ahead and I'm going to give it the name C. I'm going to name the number of operations C within the loop. That means that we can express this, the number of operations or logical operations carried out by this function or this sum as the following summation. So again, the first sum here is the one that we just worked out. It's the sum from I equals 1 to n, and on each iteration we said there was some constant number of operations, which is c. And we can see in our first transformation here, we factor the c out. And let's remember our rule here. Since c is not dependent on the index I that we're iterating over, we can factor it out. And so when we factor it out, it leaves just a 1 there. And that sum, the sum of I equals 1 to n of 1, that should be the simplest sum for us to calculate. It's the sum of n ones. Well, that's just n. So simplifying that sum away, we just get c times n. And of course, that's sufficient for us to show that it is in theta of n. Now I want to look at another algorithm related to arithmetic, that is our multiplication algorithm. And again, I'm going to restrict ourselves to integer multiplication. Here we've got 2 integers, n and m, same as before, and we want to calculate their product. Now, there are actually a number of different ways that you can compute the product of 2 numbers, n and m. And we're actually going to only look at one, and this is the one that I'm going to call the grade school algorithm. So it's probably similar to the one that you learned to do multiplication in grade school, although we're going to think of it as a binary algorithm as opposed to a base 10 algorithm, if that's what you are most used to. Actually, binary multiplication is a little bit easier, as we'll see in a second. And again, the purpose of doing this is for us to get some experience doing our iterative algorithm analysis, review of working with these summations, and then also to get a little more understanding of, well, what are the actual complexity costs of doing these operations. So we just finished looking at addition, and we determined that the cost of adding some 2 n-bit numbers together is order n. And this For the most of the time we ignore this. That's because we operate in a realm where the number of bits in our numbers is bounded above by a constant. If we're working with integers, the number of bits is bounded by 32. If we're working with longs, it's 64. The complexity of addition and multiplication really only becomes something we worry about when we step outside of the boundaries of ints or longs and into an unbounded integer class where we can get any size integers, and all of a sudden we're worried about having million-bit integers or billion-bit integers and how long it takes us to multiply them together. So if we're not really worried about that, then we're probably going to worry, or we're going to use a fairly simple algorithm to multiply two numbers like the one we have here. So again, let's take a look at it. If you recall from the grade school algorithm, it proceeds by computing a number of intermediary products, and then we sum all those products together. So we're going to do that same thing. We're going to go through each step in each iteration of our loop here. We're going to go ahead and calculate one of our intermediary products, and then once we have it, we conclude by just adding them all together. So we see here our last little step here, we're going to return a sum. We're just going to add up all these PIs that we've calculated. Okay, so again, P is going to be an initial empty list of integers that we're calculating. Same logic as in our last algorithm, we're going to calculate the number of bits. Unlike in the last algorithm where I iterated from 1 to n, that just made our calculations a little easier to work with. Because this 2 to the I is showing up here, it actually works out better if I start at 0, as we would do in implementation. So that's one small change. As before, multiplication in the grade school algorithm moves from the least significant bit to the most significant bit. So let's remember that. We're going right to left instead of left to right. We're going to again enter this loop where in each loop we want to compute one of our intermediary products. Now, if you think back to the grade school algorithm, when you're computing one of these intermediary products, you're going to take one of the bits, or if it's base 10, one of the digits of the number, and you're going to multiply it against the whole other number to get one of your intermediary products. Now in binary, this makes things a little bit easier because the bit that we're computing, so the bit that we're going to compare here will be ni, and we're going to check it. If it happens to be a 1, then we just end up multiplying 1 by m. That just gives us m, so we'll see m shows up again. Otherwise, if our bit is 0, we end up multiplying 0 by m, and that just gives us 0. That's very simple. Okay, and so we really only have these two cases. Either the intermediary product we have is 0, or we're going to take the other value, m, and again, we don't get it exactly m. Remember that again in our as we calculate our intermediary products, we keep shifting one of those products to the left as we go. Each time we compute a new product, we shift the next one over to the left. So this multiplying by 2 to the I is a bit shift operator. This is going to shift it, add I zeros there. And this is why starting with a 0 works well, because the first time we do this, we want 0 zeros, and the next time we want 1, and so on. So we'll do this if our input n is all 1s, we'll get a bunch of products here. Otherwise, anytime it's a 0, that product just becomes 0. Once we're done this loop, we've got the set of products, and now we're going to return the sum of all those products. Now I'm not going to revisit the correctness of this algorithm because as the description that I just went through was intended to map on to our understanding of how the grade school algorithm works. So if we trust in the grade school algorithm, then we've designed this algorithm to be correct. So assuming we've done that properly, let's move on to the question I want to spend more time on, which is how many bit operations does this algorithm use? So I'm not going to focus on logical operations here, I'm going to focus on bit operations. So when we're calculating bit operations, the ones that I think are going to be important for us to compute, one of them is when we calculate this value m here, I'm going to consider that as being a multiplication of this bit 1 against each of the bits in m. So that, assuming m is n bits long, we're going to assume this, computing this part of the product takes us n bit operations. Now this is a bit shift. Well, however many bits we're shifting, each one of those is a bit operation. So this one here will take us I operations. And again, we need to be sensitive to how many bit operations we're going to use to do addition. And for this, we're going to stand in from the analysis that we just looked at. We know that there's going to be a linear number of bit operations to add two n-bit numbers together. So if we have two n-bit numbers, adding them together is going to take us a constant times n, and we're going to use that in our calculation. All right, so I think I stepped through some of those ideas already, but let's look at the summations that I've come up with to express this. So let's look at this first for loop here. Again, we're going to look to the index for the indexes of our summation, so the indexes match exactly. But I just described how many bit operations this is going to take. This is going to take us n plus I bit operations, n to compute the product with m, and then I to do the bit shifting. So that's going to be the cost of the for loop here. And then we're also going to end up having a cost relative to this sum, and that one I didn't look at it as closely, but here I'm going to look back and think about the problem. So first off, let's think about the size of these products that we're going to get. The first one is actually the easiest one to see. If m is n bits long, which is the longest it could be, if it is n bits long, then the first product, p0, could be n bits long. The next product is going to be bit shifted over by 1. So if m is n bits long, the second product, pi, is actually going to be n plus 1 bits long. And of course we know that each successive product is going to be 1 longer than the last. So finally we're going to say, well, in each step we're going to be adding 2 of these numbers together. And of course, and in each step, the sum, the moving sum that we're calculating, could get 1 bit longer in each step. And so that's what's being expressed in this sum here. Even though we started out with numbers that might be n bits long, the last product might be almost 2n long after we've bit shifted over here by n minus 1 bits. So once we get to that point here where we again get this this one extra bit showing up is the carry bit that we talked about. Remember, adding 2 n-bit numbers together might result in an n plus 1 bit number. So we get an extra 1 bit showing up as well. So we're trying to be sensitive to every bit operation that we calculate. So the total then could be expressed here by this sum. So my first one, I equals 0 to n minus 1 of n plus I. All right. So how do we want to sort of simplify this particular sum? This one, there's more than one way we might be able to tackle this one, but I think this one's pretty straightforward. The first thing we want to do is we want to propagate our sum over, or distribute our sum over the 2 different terms in our linear combination here. That's going to result us with 2 sums instead. So the first one, I equals 0, our sum of I equals 0 to n minus 1 of n. And our second one, the sum of I equals 0 to n minus 1 of I. So again, we've just distributed that same sum over the 2. So we have the same index to start and end, but we've distributed it over the 2 terms. All right, that's pretty straightforward. Let's see if we can simplify those 2 as well. What can we do here? Now the first one here, that one's pretty straightforward because the n does not depend on our I, so we can move it out front. So maybe being simple here, or maybe going one step at a time, we get this sum here. This is a special sum we'll maybe get to in a second. Now this one, of course, how many terms in this sum? A tiny tad trickier than the last one. Instead of 1 to n, we have 0 to n minus 1, but it's still n. So we can say n squared operations is going to pop out here. All right, plus, now we need to think a little bit closer about this one. Let's consider a similar sum here. I've just changed us from 1 to n instead of 0 to n minus 1. And we'll maybe go back and take a look at that one in a second. But my 1 to n here, this is an interesting sum. This is the sum of all the numbers from 1 to n. And there's an interesting story that I usually like to tell related to this. And this is a story about a mathematician named Gauss. Now, Gauss was a pretty brilliant mathematician, even as a young child, and he was raised in a time where he learned his arithmetic from a priest, and this priest at the time he was fond of imbibing at the local pub. And so he would often assign his students a very hard problem for them to solve on their slates in the morning, and then he would head off to the pub to have a couple beers during the lunch hour, and then he would come back in the afternoon and check on the students to make sure they had been doing their work. And so one day, he came to class and he decided, here, I've got a nice good make work problem for them. He said, okay, take all the numbers up to 100 and add them all up. And he thought to himself, okay, that's going to take a long time. That's definitely going to take a while. I've got room for a couple beers in there. And of course, he had to go over to the pub himself and add them all up. He didn't know what the answer was. So he said, all right, get to work. And he got up, and before he got to the end of the room, Gauss put up his hand and he said, well, that's 5,050. To which his teacher was quite flabbergasted. He didn't know what the answer was himself, and he said, well, how do you know? And actually, Gauss had a clever way of solving this. So the one thing he noticed is that if you added the first and the last one together, you got 101. And I don't got it here, but if we had 99 here, if we add the next two together, you get 101 as well. And this pattern obviously continues for all of the pairs that we have. And how many pairs would we have? Well, again, there was 100 numbers, so there would be 50 pairs. And it's easy for us to see that 50 times 101 is this 500 or 5,050, the number that he indeed calculated. So actually, we can use that same logic that Gauss had to actually determine what this sum is going to be equal to as well. If we add the first term and the last term together, we get n plus 1. That's our 101. And then we want to know how many pairs are there. Well, there's n terms. So just like we had 100 divided by 2 is 50, we're going to go n divided by 2 is our final answer here. Oh, I guess I got my line a little too long here. But this version here, this is the closed form expression for what I call here Gauss's sum. This is better known as the arithmetic series. I remember it as Gauss's sum because I like to remember this little story, and once I can remember the story, I can remember the proof, and once I can remember the proof, I can remember the formula. So if you haven't actually memorized this yet, maybe the story will help you like it's helped me. In any case, we need to use this sum to help us solve this one up here, which is slightly different. Now, let's look at what's different about this sum. One, I start at 0. That means the first term I add on is 0. Well, adding on 0 doesn't do anything, so I could actually just start this sum at 1 if I wanted to. because the first term is 0. All right, so I start at 1. Now it's looking closer to this sum, but this sum went up to n. This one went up to n minus 1. What happens if we changed it to n minus 1? What changes? Well, let's think. When I add the first term and the last term together, I don't get n plus 1 anymore, I get n. And how many terms are there in the sequence? There aren't n anymore. There's n minus 1. So maybe the value that we need to write here, got our n squared plus, now our version of this sum is going to be this here, is our n times n minus 1 all over 2. All right, and then again, maybe pushing that forward just to simplify it a little bit further, we're going to get our n squared plus an n squared minus an n all over 2. Okay, so maybe I'll leave it at that, maybe push a little further, gather like terms. Maybe all that's going to be important at the end is that we have these n squared terms, and we're going to see that this is an n squared operation. We just did our first sum here. The second sum is very similar. It just had a plus 1, so I'm not going to go into a lot of detail on that. Instead, let's take a look here on the slides. I did a slightly different simplification. All right, we can see here for maybe just in closing that if we complete our analysis here, now we've combined the analysis we just did on this sum with the analysis we might do on this sum, which of course is just one slightly different than the first one, so the analysis is the same. We get a number of different terms in here. Gathering those terms together is enough for us to see that the final solution here is indeed a quadratic solution, and maybe that's all that we're looking for here. How many operations does it take? How many bit operations does it take to multiply two n-bit numbers together? Well, it takes us order of n squared bit operations, at least according to this grade school algorithm that we looked at. All right, so that brings us to the end of this video and the topic of simple iterative analysis. This is intended to remind ourselves how to use summations to analyze simple looping structures like for loops. And in the next video, I want to take that a little further. Say we get a summation that's a little trickier than these ones that we might not be able to simplify directly as we have done here. What other tools do we have at hand to find approximations on summations so that we can find a good theta bound for a summation expressing the runtime of an algorithm? All right, so I'll leave it at that, and I'll see you in the next video.